Types of hulls. Flat-bottom boat. They are generally less expensive to build and have a shallow draft. They can get on plane easily, but unless the water surface is perfectly calm, the ride can be rough because the flat bottom hits each wave. They are less stable and require careful balancing of the cargo and crew.
Hey. Yes. So last time we do full form definitions through the nice electrical twins, and then also Ronghyun Hingati. Yes. Can continue. Second question. Then my teacher then goes to the stage. Sure. Whether I if your most Oh, now, now, continuing the discussion. Topic is related with IMO solutions. So the development of autonomous buses lead to various regulatory and technical challenges. Through regulations by the International Maritime Organization prioritize the safety and safety of ships, which may result conflict in autonomous technologies. For instance, autonomous vessels require installation of cameras and sensors to capture real-time environmental data and transmit immediate
However, according to IR regulations, filming is prohibited when a vessel is entering a port, and the process necessitates a captain's command. This poses significant constraints on the our system.
아니 뭐 정에 따르면 그 자율주행 수박을 개발을 해보고 있는 것들이 되게 많은데
그래서 법이 되게 많이 개정이 되고, 근데 그래서 하는 거는 자율주행 수박이가 너무
카메라 센서를 사용을 해야 되고
그리고 상시로 데이터를 받아내야 되는 시스템을 만들어야 됩니다. 근데 항구에 들어설 때는 그 때문에 카메라를 사용하거나 아니면은 뭐 다른 프로그램을 제지할 수 있는 방안이 필요하고, 일단 우선 사람을 무조건적으로 탑승을 해야 한다고 지금 말을 하고 있고요. 그래서 네, 그렇습니다. So how based in the for advancement of autonomous technology. 그래서 네, 좋은 쪽으로 영향을 미칠 것입니다. 아니면 혹은 나쁜 쪽으로 영향을 미칠 것입니다. 자율주행 선박이라는 거에서는 사람이 아무 조종을 하면 안 되는 그런 기술입니다. 그래서 그런 측면에서 이제 좋은 영향을 끼칠 것인데 나쁜 영향을 끼칠 것입니다.
According to IMO regulation, teams must be commanders.
Yes, for this.
It stops vessels from it stops autonomous vehicles from getting the necessary information so they can be fully autonomous. So it's
What?
so, they're stopping autonomous vehicles from gathering important data.
어, understand your question is camera or sensor is
This is
It's okay if there is a person that to run. It's okay if there's only exists a person like a pilot or something.
IMO regulations says the person who could
responsibility of the ship.
Yes.
So because of filming, um, um, uh, we cannot have an autonomous system in the port, so it cannot be autonomous when it's entering the
Yes.
port, but it can be autonomous after you see.
Yes.
If there's someone, it can also be someone that stay on the boat, to not have as much to do as when we have to do everything, but we need to be here and spend.
I also have a question. Even for autonomous vessels like large carriers and stuff, when they enter the port, don't they, like the tugboats bring them inside the port? Yanes,
Ah,
like do the large container ships itself come inside the port, or are they the chunks like tugboat? Because if tugboats like bring the ships inside the port, I don't think autonomous systems are like required. So that everyone, the ship can just turn off all the controls so that the parent can some that.
그리고 국민선을 왜 쓰면 안 되는 그 항공법에 의하면 자율주행을 새롭게 정의를 할 때 아무 도움 없이 선출 그런 규정이 다 되도록 그런 식으로 예외적인 항을 주어졌기 때문에 예인선을 사용하는 게 있어요.
In the case of Silicon Cobra, so we can follow, but so good, but we also we can use radar or LiDAR. Yes. And in real situation, we usually use like radar or GPS. So I think when when we if we don't can use camera, so we still can use other percentages. So it is not a very difficult or serious problem. That we can use radar online. It can be a good effect, then we can develop good radar.
That is, I believe that there has to be more components built on the ship, so the design might have to be larger or less optimal to fit in new systems.
We have another discussion topic because time is running.
you very much. Question. Please down the discussion items and answers to the file and then share.
Yes. Thanks.
The first. Good. Yes. The tugboat, it is not simple, it's a complicated problem. Not only technological problem, but also social and economical problems. And also, depending on the port, they have a different regulations on usage of tugboat. If you have to have a tugboat assistant, it will not be a single boat. There will be a team of boat, and depending on the size of the ship. Okay. So usually for the ship owner, the captain, they want to be alone using technology and devices. But it is not only technology and capability. Union of ports, they require using of tugboat and support. Because for the shipping operation, it is faster, road. So it is take long time. It is going to the removing the tugboat assistance in the future. Right. This is my part of right. It's this. So for definition, we saw video. Continue. The plus button, both. You may say the Gobukson, the turtle ship, 3%, 3%. They have a flat bottom ship. There. If you are going to the Yellow Sea is between China and Korea. The sea is very shallow, and also the tide difference is big. So that, as I told you, that the small ships cannot stay sharp. Because if water is thrown out, they can capsize. So that for the even fish boats in operating in Yellow Sea area, they should have a flat bottom ship. So that's same as a turtle ship. So they have a pros and cons.
And require careful balancing of the cargo and crew. V-bottom boat. The V-bottom rough waters, but needs more power to achieve the same speed. Many runabouts use the V-bottom design. Round-bottom boat. It moves easily through the water, especially at slow speeds, but tends to roll unless fitted with a deep keel or stabilizers. Many trawlers, canoes, and sailboats have round bottoms. Multi-hull boat. Catamarans, trimarans, pontoon boats, and some houseboats have a multi-hull design. The wide stance gives greater stability. Each of the hulls may have any of the bottom designs described above.
비아노스는요.
스태프들이 오늘 보시더라. 어떤 그게 건너뛰기.
So turtle ship was flat bottom, but Japan ship at the same time, they have a war between Korea and Japan. Japan ship has this kind of weak type because they should come from Japan to Korea. And between Japan to Korea, there was a rough sea, big waves, and deep open sea. So that they should have a more slender and river tongue to ride over to the waves. So Japan ship was faster than turtle ship. So the turtle ship, they have a different tactics way. So they stay near the coastal area and also near the islands. And then they try to capture the Japan ship coming somehow, and then use fire guns. So in the open sea area, turtle ship cannot good way, cannot win though. So there is a story. Yeah. So we are talking about the shape of the hull. So and the differences in warships. Right. Coefficient is defined as, so this one you can see this a box of length, breadth, and depth. The outer containing hooks is this one, right? And VD is the volume of the ship. So you can say if CB is small, then ship can be slender and yes, handy. So it's a V button or flat button. You may expect that the difference. Also, the ship looks like a bulk carrier. Bulk carrier usually load heavy and low price cargo, so they don't need to have a high speed. So they want to make more cargo volume, more cargo weight. So they may have a higher value of CD. Comparing to the Navy vessel should be faster, right? So that they may have a lower value of CD. So CB is a very extreme one, rectangular function. So box is you can see. Something like similar to this one. It's like a no, it's a double box. Sorry. There is no box. Okay. And 9.9 is a Great Lake. Great Lake is, you know, where is the Great Lakes? Yes, Great Lakes. No. Do you know where is the Great Lakes? Where are Great Lakes? Yes. No. Yes, okay. Yes, okay. Say again. Baikal? The Great Lakes. Great Lakes is inside the United States, around Michigan, Chicago, near Chicago, Michigan, between Canada and United States, in the Middle East, something. Great Lakes. 5 Great Lakes there. Great Lakes, looks like an ocean, very big lake. If you have a chance to fly over the Great Lakes, you may see the size. It looks like an ocean. You can see the line. It's sky. So it looks like a bar. So the eye is blue. And oceanographic research vessel is ocean. And so that high CB, you can expect a Navy vessel. No. Low CB is a Navy vessel, no resistance, and get seakeeping and high speed. High CB is a volume ship like this one. The low speed, the turtle ship also too. for high cover purpose. So I can choose as a designer, should choose.
What's the point?
Pontoon? Pontoon is something like a box. Box. Regular box. Rectangular box. Pontoon. So they made full of boxes. What? So this one. This box. This pontoon. Then same, right? Same. Should be 1.0. Okay. Leadership section coefficient. This section coefficient is if you cut off in the middle of the shape, you see that the sectional shape of the middle, you can cut fish or body with the shape. Then B, and what is T? What is T? Yes. What is B? D, breadth of shape. What is T? Depth. D is a depth. Depth means the water line. Right? So not all depths, only depth. So the box, a rectangle is B multiplied T. Right? The arrow blue section, and then AM is area of the shape section, real section. So you may say almost one, but there is a rounded corner there. But depending on the shape, yacht has very sharp V-shaped mean section, yacht. But this is a big ship, so usually big ship has a round, almost box-shaped mid section. Almost say 0.9 or 95. T this section area. The maximum section coefficient almost the same as CM. For the small ship, like yacht usually have a wider shape towards the stern after body. In this way, not the moving curve. So that midship means length in the between middle, lengthwise middle. But maximum can be for the yachts can be find at the after body, not in the middle. So sometimes it is different. But usually big ships you can use the same. Right. Longitudinal prismatic coefficient. It is AM. AM is you see just before AM. AM. So AM is a midsection area. This area. Okay? And then AM multiplied by length, so that it is almost box, but a little bit rounded box. Corner rounded. Also the draft, only draft, not depth. It's the same D, but it should be T. Should be T. Anyway. And it's depending on, but anyway, prismatic coefficient is volume of the ship. Is saying draft there. So definition is different. Usually it goes to T. So for the full shape, it is almost 0.9 something, but for sailing or small ships, high speed can be lowered. So longitudinal prismatic coefficient and water plane area coefficient. You see this is a water plane area. AWF, water line, cutting area, water plane area, with depth line, and then B and L. Here L is length and B is breadth, right? So it's a rectangle and area ratio. So you see that full large ship and also small yacht, the numbers are different. So now we learned about coefficient, section coefficient, maximum section coefficient, prismatic coefficient, waterplane area coefficient. In old days, or not even now, the designers use those coefficients for the design. I'm trying to design a container ship. I'm trying to design a battleship, trying to design a tugboat, oil tanker. Depending on the goal, you may have a different range of. And speed. Speed is important because it is inside the contract. Otherwise, you should have a big penalty if you not meet the speed. So road is a personal lane. You already know about. He developed a new number, which is the non-dimensional speed length. He created. You already know what is efficient. It determines speed and power characteristics. He studied about ship while he's trying to find out this number. So because he needs this kind of number. So naval vessel over 10 knots, cruise number is this way, and 15 feet, this vessel at 10 knots, same knot, cruise number is higher. Usually speed ratio, so the higher is speed, same as number, but it depending on the electricity high speed. So the length of the ship. So in old days, they use speed length ratio in this. Very similar, but G is carrying. This is dimensional. You know what do you mean by non-dimensional? So we would find out this one is better to differentiate differences between different forms at speed. Displacement length ratio. You know what is displacement? Displacement. You see that displacement? Displaced water volume, right? Water volume. And displaced water is water ship and also buoyancy force of coming from the ship, right? Displaced length ratio, the ship weight, how heavy a boat is relative to its water length, fatness or slimness. And predicting, usually they go in this way. E divided by length 2. So displacement under ratio, light very heavy and very heavy. And so you see that there is a ocean small ship power and Great Lake here. You see that almost 0.9. They are the range, and this one is the displacement ratio. So numbers. So anyway, they need to have such a function and ratios. They to see check center of volume, center of buoyancy. Once again, center of buoyancy is displaced water, and then center of volume of displacement. That is a center of buoyancy. The buoyancy force is acting to point as a center of buoyancy. Total force is same as displacement, right? The point of action can be assumed as center of buoyancy, force of volume, because the water is the same. Center of buoyancy or long distance center of buoyancy. For weight, center of weight is different because weight can be have a variation. You can expect your body center of your body maybe homogeneous, then you can expect the center of weight of this building, the heavy portion there, somewhere in the staircase, or right. So heavy portion is when light. There, the cargo is loaded, then cargo is heavy, depending on the cargo type. But the center of gravity, center of it is changing. Center of is also change because the submergence, shape of submergence is different. But it is uniform weight of what? So usually the center of weight and center of buoyancy nearby but not the same. You should know about it. Midsection mark and center of rotation is similar, but it is for the area case. Volume. But when you see that center of rotation, you may have a water surface, or water plane. Center water plane be somewhere in the circle. But if you have a ship, this is also homogeneous. The yacht has a better in the center of rotation can be kind of it that add a weight without changing or entropy. Is tension center is a weight, center of weight. Maybe not in the center of the body, right? But usually the designer wants to keep in the center. Depending on the cargo loading, cannot be in the center. Center of buoyancy is also the volume of the water, displaced water. So if you have a ship, the center of buoyancy is changing, so but it is not changing. Even though ship is healing, weight is still the same, right? Because it's my body. I have the same center of healing gives you different displacement. That's why the CV. Area, yellow line, set of yellow line, see the F. Then let's design box. This kind of stitch. And need to keep it. only computers well. But when I was young, a student, I shoot myself to detection out of these curves because there is no computer predict software. We need to have a calculator only, calculator lines, so that each section here, the shape of the hull, you calculate depending on maybe draft, design draft, then you shoot the surface area, somewhere in the area, you calculate this area, this way somehow. So this is the area, integral, y, z, and this curve area. So then you so this section here, somewhere here, the value is the area, the section. And then this curve, we put this sectional area curves. This one, sectional area curve. By integrating this area, you get the volume. So much volume. So this is a displacement tool. So there is a knowledge behind, calculation behind. So we call this hydrostatic curves. We complicated one. This one is a longitudinal center of gas curve or LCF. You see that there's optimum LCD starting from length of forward to center gas. As depending on the CD block coefficient, this is a optimal LCF. And Froude number is optimal. So high leadership, probably this one higher number. We have a different LCD depending on the block coefficient. Nobody usually works with wave making resistance or CTP. It goes with the distorted resistance and this is the after body, and full body, LCF is changing. This is the light. This light.
Lines here, and from the side and from the front they look straight, right? Because they are horizontal slices of the hull. But if you look at this from the top or from the side, sort of from this oblique view, then you get a sense for the curvature of the ship as it changes from the keel all the way up to the top decks. And so now we say, okay, here's some lines. We can start to see more of how the hull is changing, what its real shape is here. Similarly, if you take the midship section plane and you take a bunch of copies of it and put a bunch forward and a bunch aft, you get what are called stations. The stations here from... Okay. So finally, if you take the centerline plane and you take a bunch of copies and you send them port and starboard, you get what are called buttock lines. And you can look at these lines and they're sort of like the lines of pressure on a weather map, right? Okay, so there... again, remembering that the body plan shows the stations that are forward of midships on the right and the stations that are aft of midships. You're looking at how much dock length do I need to actually bring my ship up to a dock, right? You got to make sure you have room enough for the entire... Okay. Beam is the width of the ship. It is almost always just the maximum beam, which is almost always... You can then calculate a plane coefficient, which is just the area of the waterplane divided by the length times the beam. So you can see here in the illustrations how much of the waterplane is actually being taken up by the ship as compared to how much station corresponds with the trim axis, again, volume. And so this is what we use this triangle for. You may have seen it with as a gradient symbol in math class, but here we use it as the volume of water that's displaced by where your buoyancy is going to be coming from, which we'll talk about later. So the bulk of buoyancy is going to be coming around midships, not so much at bow.
쪽에서 이상하게 나와요? 들었다. 들은 거.
혹시 Hello everyone, today I'll be explaining about hull forms, more specifically the proportion of the hull and lines out. Okay, let's start off understanding the hull proportions. Hull proportions play a critical role in determining the overall stability and ability of the ship. There are various types of ratios: length to depth ratio, beam ratio, length to draft ratio, beam to draft ratio. These ratios indicate the performance and behaviors of the ships. For example, a ship with a length to beam ratio has a sleek and slender design, and it has several benefits, such as higher speed. It may have less maneuverability because of its shape. As you can see, these ships have various shape hull forms. The one on the right has a very high length to beam ratio, as you can see, very sleek. Beam ratio is about the ship's leanness and its effect on maneuverability. You can see from the graphs shown here, here the length beam ratio, which is on the x-axis, the ship has reduced resistance even at various ship velocities. The concept of force relates directly how the shape of the hull impacts the speed. As the professor explained previously, the or block coefficient is the actual volume compared to the actual volume of the ship compared to the idealized rectangular block that encompasses. Ships with a larger block coefficient tend to be slower than those with a smaller coefficient, shown with the table in the middle. And the red side there, where the plot comparing
the fruit number and the block coefficient. Here's the relationship of that plot. Okay, now we come to an essential part of drawing, which is line drawing. Line drawing is the process of converting the idea and design of a 3D ship into a 2D structural plan that can be used to construct the ship or share design. This image shows the people creating the structure of the ship from construction drawings. The process involves projecting the 3D form of a ship's hull into 2D surfaces. This is like drawing the contours of a mountain or slicing a loaf of bread. Through a technique known as mold loft, naval architects map out curves, which is then used for manufacturing. Contour maps for mountains represent the 3D form of a mountain 2D image. Contour maps are simply the sum of several outlines that are created from slicing mountains parallel to the horizon, constant height intervals. Drawing lines on a ship on the same line for various sections to capture details of the whole form. The body plan shows profile the ship at various stations, which is shown here on the right side, and from the stern, which is the rear here on the left side. So if you look at the red image, the right side shows the profile at various stations, starting from the bow of the ship, which is at the front. And on the left side of the image, there's the profiles looking from the stern of the ship, which is the rear. It shows half of each side because usually most ships are symmetrical, and there's images you can put in more information. The profiles are the outlines of the hull. The half breadth view or the top view shows the horizontal profile at different heights, which is shown here in the blue image. This is also shown as a half image to save space for the drawings. And the side view, which is shown here in yellow image, shows the profile various planes divided on the center. Here are some lines from a ship. You can see body plan, the left and right image is different because to explain, the side shows profile from the rear, and the right side shows the profile from the. And as the professor showed in the last video, the lines are the lines that are cut out in the various distances from the center line. And water plane lines, water lines are the top view. They're called water lines because as a ship, the weight of the ship increases. The ship goes into water at different heights, and the lines indicate where the water meets the ship. That's why they're called water lines. Here's a video training how these lines
주소를 카피해서 파워포인트.
Hi, I'm Murphy Griffin,
I'm Madison Taylor.
and welcome to episode.
top 3 ships.
Okay, so we've sliced up our three models, and we sliced it just like you would a loaf of bread. Each time we sliced it from a different direction. Each different direction corresponds to a different set of lines. So here you can see that we generated our water lines. Here we generated our station lines, and here we generated our buttock lines. So if we look at the buttock line case, you can see that all the slices that we made were parallel with the center line of the boat. Now these lines look straight from this perspective, but when we turn it, you see that those lines are actually
parallel with the bottom side profile.
What results are the buttock lines of the boat seen in the profile view. If we do the same thing with the water lines, and we'll leave the keel behind, you can see that in this case,
Go to the Bluetooth menu.
the slices that we made are now parallel with the bottom of the boat, or with the shear, or parallel with the line of the water, and that's why these are called water lines. So seen from this perspective, you see straight lines. These curved lines in the last case, parallel with the front or the back of the boat. So they're straight from this and curved if you look along the boat like so. These lines correspond to the station lines.
That was episode 4 of Neophyte Boat Rides. Thanks for watching.
For the development cat, its lines were drawn, not actually chopping out the ships, but from the design, they would draw a line by hand. And they would use this to share the design and use it in manufacturing. Now, as CAD technology improved, people usually share the design that are made by CAD software.
We can use even paper drawings if necessary. This video demonstrate what service we can offer for design hull shape. Import initial information. Available information. It can be general arrangement plans and profile, 2D preliminary lines drawing with hull city, distance prediction, visual waves pattern, pressure distribution around hull. Streamlines show us area of the hull surface we can improve. Shape output files and documentation. Output documentation can be presented in several different documents. It can be classic lines drawing, lines and sections by customer request. This can be exactly shape design advantages. Start shape design from scratch on early stage of the project.
Is the table that records the distance offset from the baseline, which is the bottom line here, to where each meet. So the water, where, for example, where the station line and the water line meet, you get for each combination, you can measure the distance and put it in the table of offsets. The distance is written in feet, inches, and 8,000 inches. So if the distance from the baseline is 1 foot 3 feet and 3/8 of an inch, it would be 1-3-3. Okay, last but not least, this is I added this video because I thought this was interesting. This video explains why the ship's bow design is different from ship to ship.
I knew I was underwater. I just didn't realize I was this underwater. If you're stressed about your paper...
Logic says that for a ship to move as fast as possible, you should have a bow that is as sharp as possible, yet when you look at different ship designs, you'll notice that all of their bows are different. Some are fine and sharp, while others are what can only be described as dumpy. So why are there so many different bow shapes, and what possible advantages can each really have? A few months ago, I released a video about the RMS Empress of Ireland where the observant among you will have noticed the shapes of the bows of the two vessels. The Empress, as a classic ocean liner, had a straight bow which, when viewed from above, tapers in from approximately the bridge position. The idea is that it's sharp enough to cut through the water, yet it still gives sufficient width to the hull at a reasonable distance, partly for space for passengers, but mainly for buoyancy and stability. You see, if the hull was really long and thin, it would need to sit so much deeper in the water to be able to support the weight of the passengers and cargo. Not only that, but you would lose the ability to rely on form stability to keep the ship upright, meaning that you would need a massive great weight low down to keep the ship stable. This is what the old sailing ships had to do. Their rounded hulls couldn't provide the same degree of form stability, so they were supplemented with ballast in their keels. Anyway, we've now established that the bow of a ship has to be a compromise between sharpness, to reduce drag, and width, to increase capacity and stability, but what about its side profile? Again, in the Empress of Ireland video we saw two examples of different profiles. The Empress with her straight bow, which makes sense from a logical perspective, and the Storstad with a tumble home bow, which proves so devastating in the collision. A tumble home bow is one that slopes inward the higher up you get. It creates this protrusion underwater and results in a shape that is much easier to cut through heavy seas. As waves ride up over the bow, there's minimal increased displacement, meaning that it's less likely for a ship to pitch up and down. As these ships move along, they just look solid and they appear to cut through the waves rather than ride them. Unfortunately, however, as we saw with the Empress of Ireland, when one of these tumble home bows is involved in a collision, they inflict an immense amount of damage under the waterline of the other vessel, drastically reducing its chances of survival. So much so, in fact, that this very incident was the catalyst for the next evolution in the design of ships' bows, the flare. A flared bow is one that sticks out much further as you get higher up. The idea with these is that they're much better at riding waves because, as the wave approaches, the water encounters more hull, increasing the buoyancy and lifting the bow up with the wave. Where the tumble home was prone to punching straight through a wave, the flare increases a ship's ability to ride the wave. And, unlike in the Empress of Ireland incident, a flared bow is going to do a greater amount of damage above the waterline in the event of a collision, but the vessel that gets hit is at least more likely to maintain sufficient watertight integrity to remain afloat. The amount of flare does vary between ships, of course. A modern ocean liner designed for the North Atlantic has quite a prominent flare, while a huge crude oil tanker has far less. Of course, these two vessel types had some considerable differences which came into play when their bows were designed. The ocean liner needs speed and comfort for passengers, while the crude oil tanker primarily needs as much cargo space as possible, and it needs to be able to operate at a much wider range of drafts. Fully laden, a Cape-sized crude tanker might have a draft of over 25 metres, yet in ballast, you would expect less than half that. Any flaring of the bow could only occur on the part above the fully laden waterline, which, given the density of the cargo, is not going to leave much hull available. Compare that to, say, this car carrier, and you can see what's possible when the cargo is much lighter. There is so much hull above the water that you have space to not only create the flare, but also to build multiple decks of superstructure high above the waterline to protect the cargo. In this particular case, the flare of the bow is necessary to maximise the cargo carrying capacity. Without it, you'd be limited to the footprint of the underwater hull. It's the same story with military vessels, such as aircraft carriers. For them, deck space is the most important thing. Obviously, you can always use the space straight above the submerged hull, but for a bigger runway, you really want it to overhang, and you don't want water sloshing over the deck in heavy seas. The flare at the bow accomplishes both, protecting the larger deck space by allowing the ship itself to ride up and over large waves. When it comes to destroyers, however, the priority can shift. They don't need lots of space above the waterline. In fact, they benefit from less superstructure because it reduces their radar cross-sectional area, reducing how visible they are on other vessels' radar screens. Size is only one element, of course, because the tumble-home hull also has the advantage of angles. All those sharp lines and upward-facing sections mean that any radar pulses that strike the hull are going to be deflected up into the sky, so they won't bounce back to the radar they came from. A flared bow, on the other hand, would tend to bounce the pulse back towards the surface of the water, increasing the chance of it propagating back to the enemy radar. Moving back to the commercial world, the next bows to consider are those on vessels such as this OSV. While you do get some that have a flared bow, the most modern ones are tending towards this sort of inverted bow design instead. They are a little like Tumblehome in that they slope inwards as you get higher up, but the key difference is that inverted bows do not necessarily reduce their beam as you get higher. On this ship, when you reach the top accommodation deck and the bridge deck, it will still be the full width of the ship. The idea is that the superstructure is still sufficient to provide a good amount of buoyancy at the bow, so it won't dive through the waves in the same way that a full Tumblehome would. Of course, it's not going to ride the waves in the same way that a flared bow would either, but given the area of operation of these sort of vessels, that's probably a good thing. The seas are often high and steep, so having a hull that can cut through while still riding a little will make the movement much more tolerable. Moving from commercial to pleasure, we can see all the same principles at work. I've seen small yachts with straight or plumb bows, and I've also seen them with raked or a bit like flared bows, just with less curves. The rake allows more space in the hull and better.
Why the ship's designs are so different. That is the end of my presentation. Next thing. More. Okay. Don't have it outside. Start discussion session. Today, 2 weeks time. Go on to 10, 15, October 15 for the discussion session. But the sectional shape, I do myself using lines drawing. In old days, because of the no computer graphics, you may think about you are trying to make a football, making a football out of a leather. Right? Football is made of leather. You should have a designing of, what is this? 8-sided plate elements, and then stitching up together, right, to make a ball. But because the leather, the material has a flexibility, you may have a making a flat leathers and making pieces and stitching together and blow up. It can be a ball. But if you are thinking about making a football out of steel plate, how can you make it? Same story as a ship or airplane too. Right? You need to make a steel plate somehow, cutting them and bending them and welding them together to make a ball. Right? So it's not easy. should have a two-way curvature for the ball, even though there is a small piece of stipple. Okay, the other thing we can do is to check the website of companies. Come to here and show us. Okay. You can use my book. Okay. And how about KLMS? KLMS, you guys using this one? Or students are using this KLMS? Yeah. KLMS. 이해를 잘 못했다니까 이런 거 들어가 있다. 기다려 봐라. 매년 들어가서 보여.
So this is the homepage that we made for this semester. So we'll share the link through the call, and it has information about the how the class runs, and also it also has class schedule upload. Yeah, as you can see. And also it will upload the lecture note every week, and also lecture videos on the next time. And it puts to the YouTube link, so you can find the lecture video if you cannot attend the class. Right here, you can see the 2024 fall semester. All the video will be uploaded here. And regarding the term project, when you send the PPT file to us through the Kakao, we will upload.
So please upload the web page address to the Kokesh contact in the Kakao. I also need the Zoom link, Kakao. You can find out. Website. All right, see you next week. But the other week we will have a component. Right? Thank you. Tell us. 오늘 춤을 이제 아무튼 할 수 있게 해서 우리 뭐든지 할 수 있게 찾아야 그렇게 한 사람이 시인 안 해봐서 모른다 아니 그때 한테
때는 특정 주를 지정해.
아니 진짜 어느 때나 할 수 있어 항상 비어있는 걸 찾는 이게 자기 수업 시간 뭐 다른 스케줄 이런 거다 빼고 가능한 시간들을 진짜 빨리 해야 돼.